So inequations and inequalities, and there is a difference whether you realised it or not. Right? An inequation is like an equation, is what I was trying to say, is where we're trying to locate possible values of well, x usually, whatever the pronumeral is. This is an inequation which we want to solve to find the values that will satisfy this. And of course we do it just like in an equation, and there we go, x is less than minus a fifth. So some classic inequations that we have to solve. Linear ones, as I say, pretty easy. Quadratic ones. Well, yes, we sort of solve them like a quadratic equation. We sort of use the idea, what adds together, what multiplies together, so I can factorise it. Now, the common mistake here is to go, oh, well, therefore, x is less than minus 6 or x is less than 1. Of course, that's not true. All this does is finds our critical points. If you think of it graphically, whether or not you actually draw the graph is another matter. But if you think about it graphically, what we're saying is, hey, we've got a parabola here, which we know the x-intercepts are at 1 and minus 6. And it's a concave up parabola. But what we're really saying is, when is the y values less than 0? For what piece of the parabola? Now, of course, it's the piece of the parabola that's below, which has x and y values. We're only interested in the x values. So we say, well, what possible values of x is that parabola below the x-axis? Well, those ones there in between minus 6 and 1. So that's our solution. X is in between minus 6 and 1. So yes, we solve it like a quadratic, but that gives us our critical points. I think of it like a parabola. The other way, of course, you can think of it just like a number line and test points. Solution to a quadratic inequation, you're either going to be in between the 2 points or on the outside of the 2 points. It's always going to be one or the other. So here's this one. Look, when I get these ones, I don't know about you, but I hate doing negative x squareds. So I just multiply everything by negative 1. But of course, if you change the sign, you change the sign. So it becomes greater than or equal to. There we go. That now factorises. My critical points are minus 4 and 1. They're included in this case because it's an equal to as well. This time I'm saying, hey, when's the parabola above the x-axis? And this is a case where I'm on the outside. So greater than or equal to minus 4, greater than 1. That sort of an equation, I suppose, is at a 2-unit level. Okay? That could be in a 2-unit test. This type of one is now at an extension level. These ones where pronumerals are in the denominator. So we see these in extension exams. 1 over x is greater than or equal to 3. I do it by what's called the critical points method. I simply say, hey, here's a fraction. We know there are problems in the domain of fractions. What is the problem with the domain of fractions? Yeah, bottom of the fraction can't equal 0. Okay? So that's the first thing I do, is I'll look at the fraction and say, well, what would make that equal to 0? I know that's going to be a key point in my solution. So in this case, it's simply x can't equal 0. And then I just solve it like it's an equation. And that gets me any other critical points. In this case, 1 over x equals 3, so x is a third. There's my 2 critical points. I just plot them. The 0, of course, is not included because the bottom of the fraction can't equal 0. And again, I'm just asking myself, where am I on this number line? Am I in between? I'm on the outside or anything like that? So I can just test a point. So if I test negative 1, again, whether you actually write it down, you're probably doing it in your head, but you go, 1 on minus 1. Is that greater than or equal to 3? No. So I won't include negative 1. What about a quarter? That'll be in between 0 and a third. Sub that in. 1 on a quarter. Is that bigger than 3? Yeah, it is. Yeah. So I know I'm in between. But just to make sure, let's have a look on the right-hand side. I'll test x equals 1 as well. 1 on 1, is that greater than or equal to 3? No, it's not. So I know I'm in between 0 and a third. The third is included, and the 0 is not included. Okay. So that's how I approach it. I think that by far it's the easiest way of doing it. It's interesting. The majority of people will do it another way. And what they'll do is they'll multiply both sides, not by x, because you can't do that. Why can't I just multiply by x? Like,
Because it can be negative or positive.
exactly, you don't know whether x is positive or negative. And remember, if you change the sign, you change the sign. Well, if you don't know what the sign is, you don't know whether to change the inequality sign. So instead of multiplying by the denominator, they multiply by the square of the denominator, because you know that's going to be positive, and the sign doesn't change. It then creates a quadratic inequality to solve, and then they'll solve that. That is probably the most common way of solving this. The most successful way is this method of critical points. Okay. The majority of people will do it the other way, and people will get it right, don't get me wrong. But the most successful method is simply to do this, because all you're doing is saying, hey, bottom of the fraction can't equal 0, and I just solve it like an equation. Gets me the key points, and I just test. So let's have a look at another one. 2 on x plus 3 is less than 5. Well, bottom of the fraction can't equal 0. That gets me one solution, negative 3. Now I solve it like an equation. See, the advantage of doing it this way is I'm solving a linear equation. A lot easier. If I multiply by the square of the denominator, I'm going to be solving a quadratic equation. Okay, that's not that big a deal. But just imagine that the top of the fraction had algebra in it. I might end up with a cubic or something like that. So there's my critical points. I just got a test, and works out I'm on either side of this one when I test. There's my solution. So that's extension 1 level. Inequality, I said they were different. Inequality is now a problem that we're proving to be true for a known set of values. So in equation, we're finding the set of values that it is true for, whereas in an inequality, we're proving it's true for all of these possible values. Once you work out exactly what you're trying to prove, so you can manipulate what you're trying to prove as long as you use accepted laws of mathematics and don't do any illegal operations. So you can rearrange what it is you're trying to prove. Okay? But once you've decided this is what I'm going to prove, you do not treat it like an equation. Right? Once you've started your proof, you can't move things to either side. Otherwise, an inequality is a very easy thing to prove. If I could do it like an equation, and I had to prove that, say, this side is always bigger than or equal to the right-hand side, you know what I'm going to do? I'm going to multiply both sides by 0. And then I get 0 is greater than or equal to 0. Well, that's true. Beautiful, I proved it. Okay? Can't do that, all right? You can't do that. So once you've started on it, it's like you know those trig identity questions where you start with the left-hand side, you have to come up with the right-hand side. It's like that. You start with one side, come up with the other side. This is basically what you were talking about. If you want to prove left-hand side is less than right-hand side, what some people find it's easier to prove, what some people find easier is to manipulate it, right, into less than the right-hand side. So start with the left-hand side, manipulate it, come up to be less than right-hand side. Some people prefer, before they start proving, move the right-hand side over and have this new expression, left-hand side minus the right-hand side, because they find, hey, it's easier to always show something as negative or something as positive. And so rather than showing left-hand side is less than right-hand side, they show left-hand side minus right-hand side is less than 0. Because once they prove that is true, once we know that's 100% certainly true, now I can start moving terms again. Okay? Of course, the third way of doing it is to start with the left-hand side, manipulate it into some new expression, go with the right-hand side, manipulate that into a new expression, and prove that. So start with a known result. Okay? If you start with a fact and manipulate it, then it's still got to be a fact. So if I have to prove this, I know the information they've given me is that x minus y is always greater than y plus z. We have to prove y is less than x minus z on 2. So I'm going to start with a known fact. X minus y is greater than y plus z. Because I know this to be true, I can move terms like an equation, because it's true. So why don't I make y the subject? Let's see what happens. So minus 2y is greater than z minus x. Divide by negative 2, but if I change the sign, I change the sign. So y is less than x minus z on 2. That's what we're trying to prove. So what I'm basically saying is you can only move terms from side to side from known facts, things you know to be 100% true. If it's what you're trying to prove, you can't, because you don't know that's true yet. You're trying to prove that. In this case, I started with something we knew to be true, so I could manipulate it, come up with the result. Move everything to the left. We know A is greater than or equal to 0. B is greater than 0. We have to prove that AB times A squared plus B squared is always greater than or equal to 2A squared B squared. Whew, that looks tricky, so I'm not going to do it. I'm going to move everything to the left. I'm going to attempt to prove this is always positive. Because once I can say with 100% certainty that that's always positive, once I know it's a fact, I can move terms. So I've started with the left-hand side minus the right-hand side. And if I factorise that, you'll notice there's a common factor of AB there. A is positive, B is positive, and I've also got A squared minus 2AB plus B squared. Well, that's A minus B squared. So A is positive, they told me that. B is positive, they told me that. A minus B squared, that's got to be positive. So yes, I now know with 100% certainty that this expression is always greater than or equal to 0. Now that I know that this is true, I can move the 2a squared b squared to the other side. Therefore, that must be true. And of course, same sort of idea is that squares are always positive or 0. We know that. So I'm going to show that if a, b and c are always positive, then a squared plus b squared plus c squared will always be greater than or equal to ab plus bc plus ac. I know, I'm starting with a fact. I know that a minus b squared is always greater than or equal to 0, because a square is always positive or 0. If I expand that out, I get a squared minus 2ab plus b squared is greater than or equal to 0. I know that to be a fact, because all I've done is expanded out the left-hand side. Because it is a fact, I can move the 2ab. I now know a squared plus b squared is always greater than or equal to 2ab. A and b, they were just letters I picked. I could have picked any letter. So a squared plus c squared must be greater than or equal to 2ac. In fact, b squared plus c squared must be greater than or equal to 2bc. They're just letters. Well, why don't I add those three together? So 2a squared plus 2b squared plus 2c squared is greater than or equal to 2ab plus 2bc plus 2ac. Divide everything by 2. That's got to be true.